Sunshine.
The Computer Museum in Boston provides a unique opportunity to encounter the hardware of the computer revolution in new and exciting ways. But why celebrate such a commonplace machine?
According to a classical definition of a machine, it is something, a device that somehow channels the forces of nature through a mechanism into a very specific purpose. A computer does not fit that definition. A computer's purpose is only specified when you load a piece of software into it and execute that software. Now, that shift in the fundamental nature of machinery was not really understood by the inventors of the computer.
So software was at the heart of understanding these new general-purpose machines. But it's often been ignored by the historians.
The history of computing until now has been dominated by the milestone machines like the ENIAC or the IBM 360 or the Apple II or something. Now, software is also a cumulative process. Today's software developers build on the work of their predecessors, and there's quite a bit of that. You don't start with a completely blank sheet of paper every time. But how do you talk about a milestone like that? It slips through your fingers when you try to grab it.
Engineers were building a digital computer because they could see that was the coming activity, and they wanted to learn something about digital computers, so they just built one. And one day my boss came over to me and said, "Gene, do you want to be the programmer for this computer?" I said, "What's a programmer?" He, being a very nice guy and a very competent engineer, said, "I don't know what a programmer is, but I know we need one. How would you like to be it?"
So what are the milestones in the history of software? Who were the first programmers? How has their job changed? And will we need them in the future? The birth of modern computing is said, mostly by the British, to have started with Colossus. It operated at the top-secret Bletchley Park in Buckingham and was designed to crack the enemy codes of World War II. The war was also an impetus to the development of ENIAC, considered, mostly by the Americans, to be the first computer. ENIAC was initially designed to calculate the firing trajectories of field guns. How would the angle of the gun, shell size, and wind direction affect where the shell would fall? Kay Morkley was one of the first people to work with the machine.
The ENIAC itself was 80 feet long, and because it had 18,000 vacuum tubes that generated a lot of heat, so the biggest noise that you could hear in the room, however, were blowers that were in the ceiling that were supposed to carry off the heat from the vacuum tubes as they heated up. The machine was not turned off at night. It was kept going night and day because a lot of the tube failure would occur if tubes were turned off and then turned on again.
ENIAC was more like a mechano set where you put pieces together to make a machine of your problem. So you put all these pieces together. You're more like an architect. And you would pick up the trays for the numbers to go across and the digit trays in the bottom. Each one weighed 42 pounds a piece. So I was never in any better shape in my life when I picked those things up. But programming for the ENIAC was not like programming today at all. It's more like building a machine.
Colossus and ENIAC are said to be computers because they were general-purpose machines. Their purpose was changed by changing their wiring.
The machine was not wired specifically for a problem. You actually had to do the wiring for each problem. However, say once you had set it up to run trajectories, you could run 10 million of them. If you had a brand new problem, which had nothing to do with trajectories, then you would just pull out all the connections that you already had and then start off with making new connections, and you'd also reset all the switches.
We know that the ENIAC was very far away from the kinds of things we call a computer today in terms of its logical structure, but it pointed the way toward that. It did have a kind of general purpose ability. You could rewire it. You couldn't program it, but you could rewire it very tediously to do lots of different things.
The generality of ENIAC was demonstrated on a secret research project.
I can't remember when we first became aware of the fact that we weren't with a machine that was just going to do trajectories. When the people came from Los Alamos with the very, very first problem, we thought, oh, well, we're just testing it. This is what they told us. This was a test for the ENIAC.
I was on the machine that night they dropped the bomb on Hiroshima. I'll never forget that night. I never went to bed because when I got home, the newspaper said all what this thing was, and I realized I put two and two together that I had been working on the Manhattan Project and people from Los Alamos. And I'll tell you, I couldn't sleep after that.
Here was a problem that was so immense that it took every switch on the machine. So we thought, well, this is a tremendous test, but once that's finished, we'll go back to doing trajectories. Actually, it never happened that way. Once people found out about the machine, various professors from different parts of the University of Pennsylvania had problems which they had been storing up, and if I ever have a machine, I will do this, and they brought them in and tried to run them.
Despite being new general-purpose machines, they had one important failure.
The ENIAC and the Colossus had a lot of limitations, and I think that that's worth keeping in mind. One of the biggest limitations for the ENIAC, which is the machine I know the most about, is that it really had to be literally rewired for every new problem. The only thing that made it a little easier is that instead of having to cut the wires and solder them again, you had plug boards, kind of like an old telephone switchboard. You could draw out diagrams of the wiring for a new problem and then bring it to the machine, but while people were doing the plugging, the machine was of no use. The stored program is the key to the modern computer age because it allows the program itself to be manipulated inside the machine as though it were just any other piece of data. Now, why would you want to do that? Well, ultimately, the reason is that you can make a computer program operate on another computer program.
Like all good amateur movies, this one tells a story. The EDSAC had begun to work in May 1949, and we had developed a system of programming based on the use of a library of subroutines. The film was made for the first joint computer conference held in Philadelphia in December 1951, and it was, I think, the first film showing the operation of a stored program computer to be made.
EDSAC wasn't constrained by how it was wired. It had a memory where it could store temporarily a sequence of machine instructions.
The EDSAC made use of a serial ultrasonic store. consisting of 32 tanks. It was possible to exhibit the contents of the memory on a cathode ray tube, like this. There are 16 lines. The presence of a 1 is indicated by a bright dot, and the presence of a 0 is indicated by the absence of a dot. You will see a program tape being read and the instructions filling up one of the tanks from the bottom. I hope that this old film will give you some idea of what computing was like in 1951.
Programs, of course, would need programmers.
Every single thing that a computer does has to be specified in the tiniest detail. Even to add two numbers together, you have to tell it where to get the two numbers, where the position of the decimal point is, how to shift things, what to do with carrying a digit, and all of that. That all has to be specified, and it's specified usually in a code that is usually lists of binary numbers, that is to say ones and zeros, or there may be a slightly symbolic code that replaces the binary ones and zeros, but you still have to specify every step. And that is an extremely tedious job.
Most programmers until now had been maths graduates, many of them women. But now it seemed it was jobs for the boys.
At that time, the help wanted ads for men and women were different. And under women, secretaries, clerks, nurses, housekeepers, whatever. Certainly nothing that was going to be relevant as far as I was concerned. So I started to look in the men's section. And there, I looked under programmer, no such thing. The term, while it existed, didn't exist enough to get into the help wanted section. So what I had to do was look under engineer and then read the description, because the description could be of programmer.
Joyce Curry Little worked on some of these early programs.
The level of detail of machine language programming was so great that many people spent months and months and months writing code, deciding what code to be written, and then embedding that into the machine. And so the amount of labor was intensive.
Nowadays, there's no need to communicate directly with the computer's hardware. An English command, like send mail, might involve several translations, but the translations are done by the machine.
Very true. That wasn't very loud. Try again, please.
The command might initiate a section of program which was written in a high-level programming language. The machine might then translate or compile this into another symbolic language. Now, at a lower level, it includes precise hardware instructions, and eventually this is transferred into the binary code of just ones and zeros.
Prior to the advent of significant programming languages, people had to write in much more detailed instructions for the computer. And the chances of making an error were about 95%, that you probably would make many errors in the process of writing this very unreadable, constricted type of notation.
This is one of the other programmers coming in for her results, but she must have made a mistake. We used to use for debugging a trace routine that would print the function letter of each instruction as it was executed. Our programmer collects his results. He is joined by the mathematician, and apparently all is well.
The longer the program, the more likely it was to have an error. And when you got programs that were 10,000 or even 100,000 instructions long, they would have so many errors in that it would be very difficult indeed to get them correct.
One wrote a great deal less if you had a formula of the form A equals B times C plus D divided by A, that could end up as 10 or 20 instructions that you had to convey to the computer. And the way in which you used a higher level language was simply to write A equals B times C, whatever the formula might be.
What a high-level language did was to give you a productivity lever, so that by writing 1/10 as much code, you could actually generate the same number of machine instructions, and consequently you would make only 1/10 of the errors.
The program in a higher level language was simply far more readable for not only the person who wrote it, but somebody else who might try to read it and check it. If you write a formula that's fairly clear, if you say compare A and B, or if A is less than 5, then do something or other, that's just a great deal more readable and understandable and less likely for error than the machine code would be.
From the 60s onwards, computing saw the development of a bewildering range of high-level programming languages. Prominent amongst the most popular of the early languages was Fortran. This was aimed at helping with problems in engineering and science.
It was really quite a thrill when we heard that we were going to be receiving instruction in Fortran and eventually a compiler in Fortran. And so we all looked forward to it because it was a new language to learn, and we thought that it would save us all a lot of time. Our early experiences were hilarious. We had a small group of about 8 people attending a class with a young instructor from IBM who had learned Fortran but didn't necessarily know assembler or machine language. And so together we learned a great deal because every time he'd present a new language, we'd present him with what was underneath it.
The binary for a simple task of adding 1 to a series of numbers is meaningless to the non-specialist. The assembler for the same task was shorter, but no clearer. However, the Fortran equivalent shows a major reduction in the number of instructions. Now, programmers weren't just maths graduates.
Prior to Fortran, the number of programmers was relatively limited. I don't have a number for you, but perhaps it was something under 2,000 people who knew enough about, in those days, mathematics, logic, and computing in general to write programs. The minute Fortran worked, the minute it was shown to be as efficient as, native coding, if you will, all of a sudden there was a whole new class of programmers. There were physicists, chemists, mathematicians, engineers of all kinds. And so instantly you empowered tens of thousands of people because the machine could now be programmed, and we keep using that term. But it could be structured to solve a class of problems by people who understood the problems, not people who understood computing.
Scientific programming languages had proved very successful, but there was a problem that there were quite a number of different languages supported by different manufacturers.
The business and government sectors were now looking for a language suitable for their domain.
One of the problems the American government was experiencing that every time they outgrew a machine, they had to reprogram all their existing computer programs. That was very expensive on the one hand, but also it could be very disruptive while they were changing over from one machine to the next. So the idea of having a single language that they would write all their data processing applications in, that's COBOL, would be a great economic advantage to them, saving all that cost and disruption.
Fortran and COBOL are still dominant languages today. But these are just 2 popular languages amongst hundreds, possibly thousands, which have developed. Despite the power and advantages of these new high-level languages, the 60s saw the arrival of some serious problems.
In the 1960s, as hardware prices were dropping, people started observing that software costs seemed to be going ever upward, especially as projects got bigger and more complex. It seemed to be becoming increasingly difficult to bring a project in on time, on budget, and more often than not, it was riddled with bugs, some of them just annoying, some of them absolutely disastrous. And as this happened more and more often, the label software crisis started getting bandied around.
Was the ever-expanding population of programmers now missing an essential sense of order and structure in what they were doing?
Spaghetti code is the name, colloquial name, given to a picture of the structure of a computer program, which has bits and pieces everywhere, branches going here, there, and yon, jumping over each other, lines crossing each other, and it becomes just a mass of conglomeration of lines, and it looks like a bowl of spaghetti.
Some felt new approaches to code production were needed. They suggested that these approaches could only be found in the maths, science, and engineering disciplines. They hoped new structured techniques would help programmers generate efficient and error-free code.
As time went on, people tried to call this an engineering discipline. Have used the term software engineering, which I personally don't like, because as far as I'm concerned, software engineering is simply a shorthand way of saying write good, efficient programs within budget and on time. And that's what people consider the engineering rubric. Now, there are not yet the techniques to write programs very quickly that will be very efficient and won't have any errors. The techniques simply don't exist yet.
If you look at what engineering is, both now and in the past, while certainly it has used and benefited from mathematics, from formalized techniques, etc., it has also been at its core a creative enterprise which uses intuition and what's been called by some engineering judgment just as much as it makes use of science-based techniques and mathematics and all of that.
Kathy, can you hear me okay?
Yes, can you hear me okay?
Yep. Okay, you can start the test. Why don't you go ahead and...
Today, a new piece of software may have mathematicians and engineers working on it, but the team will also include domain specialists, psychologists, and human-computer interaction experts.
So, Kathy, I think you ran into a bug. So why don't you hit stop?
Okay.
And why don't you try and find some information about Domino?
Okay. Well, this might be the appropriate place.
Yeah, right there. See what she's doing right there? What she did is she went in and she authenticated, and she was carrying Anonymous, but then she went in and tried to do something that she wasn't capable of and got bombed out.
Did she log in again?
Yeah.
She did? With real credentials?
Yeah, the whole 9
But the
yards,
password didn't work?
Right. Is there a possibility she can go back and look at that part where she just was?
Kathy?
The more diverse a team can be, the better. So if you've got people who are artists or visionaries or people who just like to come in and labor, if you get the right mix, that's the most important thing, because it's all there, and it's a very creative medium, and it tends to attract introverts.
A different database using...
I've spoken to a number of project managers who told me that they actually prefer to have a mixture of these two views. And indeed, I think that any historically realistic conception of technological practice would include attributes from both those perspectives, from both the artist and craftsman and the scientist engineer. And that seems to be, in fact, what a lot of project managers are trying to achieve.
It also tends to be very interactive. There's a very hard to be on a team and not interact with people. And I think it's a very special type of collaborative creativity that goes on in most teams. And I think that's what keeps people involved. It's a fun place to be most of the time.
At the very beginning, software was considered an art, not a science, not engineering, and so forth. Software is just very difficult to do. In my view, it's still an art. It's not a science. Whether it's engineering or not is a point one could debate ad nauseum, and I just prefer not to debate it.
Perhaps there's no need to debate it. Some have suggested that we're now reaching the final milestone in the history of software.
Okay.
One of the interesting threads that runs through the entire history of computing from the first days of programming languages was the notion that once you develop these languages, it would be the so-called end of programming. You wouldn't need anyone to do that anymore because people would simply walk up to a computer and program it themselves.
I really feel as if I knew ENIAC inside and out. My little home computer, I call up these icons, and most of the time I can't figure out what the heck they're telling me to do at all. So I just skip them. I really don't understand a modern computer the way I should, and I don't even care.
They wouldn't call it programming. They would just use the computer, and in fact they would be programming it, but it would be so easy that no one would be aware of all this other stuff going on. Well, it's a thread that runs through the history, and it's never happened.
Oh, this field has absolutely been peppered with searches for holy grails from its very inception. From the moment that somebody decided writing ones and zeros was not a pleasant way to have to spend one's time during the day, to assembly languages, to symbolic assembly languages, to high-level languages, to very high-level languages, to structured programming, to object-oriented programming. There's always a new paradigm which is going to be the salvation of a human being communicating with a computer to get a task done.
If anything is learned from the history of computing, it's that some of the most exciting and important developments will come not from changes to hardware, but from developments in software.
I suspect it's like any other part of civilization. The modern person thinks how primitive you were back then when you didn't think of it, but they don't understand that they're standing on the shoulders of giants who slogged through the mud and did things in prior years that makes them look good.